All right, first up, let's go ahead and talk about our first data structure, a linked list. So a linked list is a linear data structure that is comprised of nodes. So each of these rectangles you see here is a node. And each node has two fields, a data field which can store any type of data, as well as the next field which references the next node within the list. And if there is no next node, we just go ahead and set it to null. Now when you combine a bunch of these nodes together, you end up getting a linked list. One last thing to point out before we start the code is that a linked list must always maintain a reference to the first node. So let's go ahead and call this field a header. So the header just references the first node within the list. And if you take a look at the last node within the list, you'll see that the next field is equal to null, symbolizing that we've reached the end of the list. Alright, so a linked list is usually implemented using two classes. The node class, which is responsible for our node creation, and our linked list class, which is responsible for manipulating the references to the nodes. So starting off with our node class, so our node class has two fields, the data, which can be of any type, and the next field, which is always supposed to reference the next node within the list. So going over our node constructor, our node has one param, the data param. So this is going to be the data that we want to insert within the node. And all we do within our constructor is initialize the data to the data being passed in. And then we initialize next to null. Alright, so moving on, let's talk about our linked list class. So our linked list class has two fields. We have a header, which is always supposed to reference the first node within the list. And we also have the size, which is supposed to keep track of the number of nodes within the list. Going over the constructor is pretty simple. We just initialize the header to null, and then we initialize size to 0. And this is because initially our linked list is going to be empty. Alright, so moving on, I want to talk about how we can go about adding to our list. So we're going to start off with our prepend method. So our prepend method simply adds to the front of the list. So it has a data param, the data that we wish to insert in front of the list. And let's say we have an empty list, and let's say that I want to prepend 1, for example. First step, we go ahead and create the node that we wish to insert in front of the list, and then we go ahead and save the reference to the current first node. In this case, our list is empty, so it's just going to be null. And then finally, we go ahead and set the header to reference n. And since we successfully inserted within the list, go ahead and increment the size. Executing again. This time, let's go ahead and prepend 2, for example. First, create the node that we wish to insert, save the reference to the current first node within the list, and then we can go ahead and have our header reference the new first node within the list. And since we successfully inserted within the list, we go ahead and increment the size. So that's our prepend method. Let's go ahead and talk about our append method. So our append method is just like our prepend method, except that instead of adding to the front of the list, we're going to add to the back of the list. So same method signature as our prepend method. We have our data param, the data that we wish to insert. And there are two cases we should consider when implementing our append method. In either case, the first step is to always create the node that we wish to insert. So let's say I want to append 5, for example. So going over case 1 first, what happens when the list is empty? Well, in that case, you just test to see if the header is null. If it is, the list is empty. So just set the header to reference n, and then we can go ahead and increment the size. Now let's go over when the list isn't empty. In the case where the list isn't empty, we're going to have to traverse to the last node within the list. So start at the head of our list, and we want to keep advancing to the next node until we've reached the last node. So executing our while loop, is current.next not equal to null? It is, so we advance to the next node. Executing again, is current.next not equal to null? It is, so we advance to the next. And we keep repeating this process until we reach the last node within the list. And all that's left to do is go ahead and add the newly created node to the end of the list. And then we can go ahead and increment the size. Alright, so we know how to insert within the front and back of the list, but how can we go about inserting between the first and last node within the list? So let's start to talk about our InsertAt method. So our InsertAt method has two params, the data that we wish to insert and the index of where you want to insert the node. So our InsertAt method has a couple of cases we should consider. What happens if the index we want to insert at is out of bounds? So the index is considered out of bounds if the index is less than 0. so if it's a negative index, or if the index is greater than the size. So if this is the case, we just print that the index is out of bounds, and we just return from the function. If that is not the case, these two upcoming cases should sound familiar. So what happens if I want to insert at index 0? Well, index 0 sounds a lot like adding to the front of the list. So we just go ahead and invoke our prepend method. Now what happens if I want to insert at size? Well, let's just take a look at the diagram. So if size is the same as index, it looks like you want to insert at the end of the list. So we already covered that example, so we just go ahead and invoke our append method. But now what happens if I want to insert somewhere between the beginning and end of our list? So using the same diagram, and let's say that I want to insert 5 at index 2. Well, first step, we go ahead and create the node that we wish to insert. We then need to traverse the list, this time maintaining 2 references. The reference to the current node that we're at, as well as the reference to the previous node. Next, we'll initialize our counter that we'll use to track what node that we're on. So just our standard loop, we want to keep going up until we reach the position where we want to insert. So first, we save the current reference, we then advance the current reference to the next node, and then we increment the count. Executing again, save the current reference, advance current to reference the next node, and then we increment the count. And once we finally reach the position that we want to insert, we just set n.next to reference current, and then we set prev.next to reference n. And since we successfully inserted the node, we just go ahead and increment the size. Alright, so now let's move on to our delete method. So our delete method is pretty simple. We have our data param, the data that we wish to delete, and there are a couple of cases that we should consider. So the first case, what happens if the list is empty? Well, we've covered this like 1,000 times by now. If the header is null, that means the list is empty, so we just go ahead and return. There's nothing for us to delete. Now what happens if the data that we wish to delete happens to be the first node within the list? So the data at our header is equal to the data we wish to delete. We just advance our header to reference the next node within the list. And after we successfully deleted the node, we can go ahead and decrement the size. Now, if you're paying attention to the diagram, you might be saying to yourself, hey Pedro, that node isn't deleted. You just moved the header to the next node. Well, since there is no reference to that node anymore, the garbage collector will go ahead and delete that node for us. Now, dealing with the third case, which is what happens if I want to delete anywhere else within the list. So let's say that I want to delete the last node, for example. So we're going to have to traverse the list, keeping track of 2 references, a reference to the current node that we're at, as well as a reference to the previous node. So is the current node that we're at not equal to null? It is. So we check to see if the data we wish to delete is at the current node we're at. It's not. So we go ahead and save the current reference, and then we go ahead and advance to the next node. Executing again. Is current not equal to null? It is. Is the data that we're looking for? It's not. So we go ahead and save the current reference, and then we advance to the next node. Executing again. Is current not equal to null? It is. Is this the data that we're looking for? It is. So we go ahead and remove the reference of the node from our linked list. And since we successfully removed the node from our list, we can go ahead and decrement the size. And then we could go ahead and return from the function. And since there is no longer a reference to that node within the list, the garbage collector will eventually go ahead and delete that node for us. So moving on to our last and final method I want to cover. Let's talk about how we can go about printing our list. So printing our list is pretty straightforward. If the list is empty, there's nothing for us to print, so we just go ahead and print that the list is empty, and we just return from the function. Otherwise, if it is not the case, it's time to traverse the list. We first start at the head of the list, and we want to keep going until we reach the end of the list. So is the current node null? It's not. So we print what's at the current node, and then we advance to the next. Executing again. Is the current node null? It's not. Print the data at the current node, and then we go ahead and advance to the next. Executing again. So is the current node null? It's not. So we print what's at the current node, and then we advance to the next. Executing again. Is the current node null? It's not. Print the data at the current node, and then we go ahead and advance to the next. Executing again. Is current not equal to null? In this case, this fails, so we get kicked out of the loop, and all that's left to do is go ahead and print null. Alright, so now I want to talk about the big O of our methods. So big O is the worst case scenario when running these methods. So if I was to talk about prepending to the list, the time complexity would be constant time. Why? Because our linked list always has a reference to the front of the list, so we can always add in constant time. Talking about the append method, the time complexity of our append method is big O of n. Since we always have to traverse to the last node within our list in order to insert at the end of our list. Moving on to our InsertAt method is also big O of n, since the worst case would be adding to the back of the list, which so happens to invoke our append method. Our delete method's worst case would also be big O of n, since the worst case would be if I wanted to delete the last node within the list. In that case, I would have to traverse to the last node to delete. And then finally, our print list method, which obviously we would need to traverse to each and every node within the list in order to print. So this will obviously be big O of n as well.